In May 2025, a Google DeepMind system rewrote low-level code powering its flagship model, Gemini. It targeted a matrix multiplication kernel, making it 23% faster. That single optimization trimmed roughly 1% off the total time required to train Gemini itself. This is not a forecast or a metaphor. It is a logged engineering commit, a receipt proving that an AI has already improved the software infrastructure used to train its own successor. We have entered an era where machines are actively optimizing the code-level foundations required to build more capable versions of themselves. To understand the scoop of this trend, we look to a June 2026 report from Google DeepMind titled From AGI to ASI. The report addresses the specific engineering gap between human-level AI and superintelligence, a system that can outperform entire coordinated organizations of experts. While the public debate often centers on whether a singularity is inevitable, this report treats the path past human-level intelligence as a series of engineering hurdles rather than a prophecy. Superintelligence is unlikely to arrive through a single magic mechanism. Instead, it is being built across 4 independent roads, all of which are currently under construction. This framework is critical because a true intelligence takeoff won't just follow one path. It will compound as the system travels all 4 of these roads at the same time. The first road is compute-efficient scaling. It focuses on routing intelligence precisely rather than simply building larger models. Think of a hospital with hundreds of specialists. For any patient, a triage nurse wakes only the 2 or 3 doctors actually relevant. You get the knowledge of the whole staff at the running cost of a small clinic. In AI, this is the mixture of experts architecture. The model learns a vast range of data, but activates only the specific subsections needed. Take DeepSeek v3 as the benchmark. It has 671 billion parameters total, but activates only about 37 billion for any single chunk of text. Roughly 1/18 of the model fires for each action. By engineering a more efficient routing system, researchers expand capability while mitigating the overhead of brute force physical compute. The second road involves architectural changes, moving away from current engines. It is the difference between breeding a faster horse and inventing the car. The most significant recent shift is test time reasoning, seen in models like O1 and DeepSeek R1. These models think before they answer, allowing users to buy higher levels of intelligence by allocating more processing time. We are also seeing the rise of state-space architectures like Mamba, designed to solve the structural bottlenecks of today's chatbots. This chart contrasts the two. Current transformer models hit a wall because processing costs rise quadratically. Mamba, however, processes data in linear time, staying efficient even at massive scales. Superintelligence will not just be a larger version of today's models. It will likely run on mathematical engines designed for far greater efficiency. The third road is recursive self-improvement. It began as a 60-year-old thought experiment, the idea that an intelligent machine could design a better version of itself, which in turn designs the next. Data shows this is happening. AlphaEvolve Scheduler has run inside Google's data centers for a year, recovering 0.7% of global compute. It also multiplied matrices using fewer steps, beating a 56-year-old algorithmic record. METR tracks the task horizon, the length of a task an AI can reliably complete. That horizon is doubling every few months, signaling exponential growth. However, most growth curves eventually bend into an S-curve, hitting a plateau. The self-improvement loop is real and measurable, but it currently represents a steep, fragile slope rather than an inevitable explosion. The final road is group agency. Like an ant colony, superintelligence may not be a single mind, but a population of immensely coordinated agents. In this model, swarms of AGI-level systems coordinate, divide labor, and check each other's work within a digital economy. These digital collectives have advantages no human organization can match. They can spawn copies instantly, share experience at massive bandwidth, and halt operations upon completion. We are now seeing the first attempts to define multi-agent scaling laws, the mathematics of how group intelligence grows as you add more agents. The bottleneck here is coordination. Without precise protocols for managing how these agents communicate, a swarm of thousands just creates noise rather than intelligence. If that coordination can be engineered, superintelligence might look less like a lone computer and more like a perfectly synchronized digital corporation. When we look at these 4 roads together, they form a braided network rather than 4 separate highways. This forces us to move past the image of a single vertical line on a graph, representing a specific date for superintelligence. The resilience of this approach is what makes it so significant. Progress doesn't require all 4 roads to be perfect. Efficient scaling provides the compute needed for massive agent swarms, and those swarms, in turn, are the most likely tools to discover the next architectural evolutions. ASI is best understood as a network of partial, overlapping paths, a reality that is harder to dismiss and far more difficult to predict. Recall that AlphaEvolve recovered less than 1% of global compute. In most industries, that is a marginal gain. But we are looking at a system where the doubling time for capability is measured in months. When a system is riding an exponential curve, fractional gains compound so aggressively that the word tiny ceases to be reassuring. Small margins are only small until they begin to compound. Subscribe to follow our look at whether these roads will hit physical walls in the next episode.